Okay, this is 2008. So it gives us this function 2x over 1 plus x squared. And as it's right, the first four non-zero terms in the general term for the Taylor series about this. It wants to know whether something converges or not. It asks us to write something about the natural log of 1 plus x squared. It gives us information about this whole derivative thing. And then down here, without even looking at it, I know it's about error, right? It's saying something about absolute value and the difference is less than something. Again, I don't even need to read that. This is showing me that the error, you're finding some rational number a such that this is true. So part D is tricky, but I think the other three parts are kind of not basic, but they're working with something that we certainly have talked about. So part A. Part A says, write the first four non-zero terms and the general term for the Taylor series. Okay, when you look at this guy, you kind of have to just know, man, that's geometric. Okay, that's an a value of 2x and an r of negative x squared. All right, it fits the form a over 1 minus r. And again, you can go through this as many times as you want. You have to know 1 over 1 minus x is 1 plus x squared plus dot 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 x to the n, right? That is the basic power series, and this is just some kind of substitution into that, okay? So if we wanted to write out what 2x over 1 plus x squared is, that's just 2x, and then times this by a negative x, so a minus 2x cubed plus 2x to the fifth, okay, minus 2x to the seventh, however many you want to do. Oh, I shouldn't say that. Let's just say 4. All right, there's 4. And then plus dot, dot, dot. It's an alternating series, okay? And there's a 2x out in front times x squared to the n. Now there's a variety of ways to write this, right? You can leave the 2 chill, and you can put the x in, right? X to the 2n and then add 1. You could do that. That's what they do in the key. I don't know if it's necessary. I kind of like this. Okay, but that's part A. Part B. Okay, it says, does the series found in part A when a value at x equals 1 converge? So can you find f of 1? And you say, of course not. You can't do that. What's the interval of convergence for a geometric series? For a geometric series, we know that this is for sure what happens. And so we need to set negative 1 in between negative x squared. Okay, if we multiply everything by a negative, that negative just switches everything and flips the inequalities, and so the whole thing just turns into this, which is the same stipulation. But this, if we like x squared can't, I mean, it for sure is non-negative, but then you take the square root, you introduce it again, and you get the whole thing right back to where we actually knew it was to begin with. If we want negative x squared to be between negative 1 and 1, we need x to be between negative 1 and 1. So no, we can't do that. 1 is not in the interval of convergence. Okay? Part C. Part C is telling you something that you already know. This is the weird part. I don't understand why they do this, but like, hey, the derivative of the natural log of 1 plus x squared is this. So why don't you use that information and write the first four non-zero terms of the Taylor series for this? Well, fine. It just feels like it's too much information and it might actually confuse you. What they're saying is that if you know this is this series, and you know that the integral of 2x over 1 plus x squared dx is the natural log of 1 plus x squared, then how can you get the series for the natural log? Well, you could just integrate this. So then the natural log of 1 plus x squared has to be just the integral of this term, which is x squared, increase the power by 1, divide by the new power, minus 1/2 x to the 4th, plus the 3rd, x to the 6th, and they do want 4 of them, so I got to keep going, and then minus a 4th, x to the 8th plus dot dot dot. And if we integrate this last guy, do we need the general term? Oh, look at that. We don't need the general term. It just says right the first 4 non-zero terms. But I'm going to claim we already knew this. Again, you need to know that 1 plus x is already known to be this, because it's one of the Maclaurin series that you memorize. And so natural log of 1 plus x squared is just putting an x squared into here, and hopefully like put an x squared in here, boom, x squared in here, boom, x squared in here, boom, x squared in here. Got it. Right? We know this. So I'm not sure we really even need to make this connection with this original function to show this. We derived this in class, that the natural log of 1 plus x is of course integral of 1 over 1 plus x. So you can do this either ways. You can just know this substitution and get to here, or you can integrate and get to here. They wanted you on part C to do this, but it's not necessary to do it exactly the way they want. Okay. All right, this last one is a really hard one, part D. I don't like it at all because it feels more tricky than it does everything else. So use the series found in part C, right? So it's telling us to use this to find a rational number a such that a minus the natural log of 5/4 is less than 100. Okay, so it wants the error to be less than 100. We're going to use 5/4, but if you're using the natural log of 1 plus, well, 1/2 squared. Again, how do you know that? Well, you just got to look at these two things. Natural log of 5/4 and 1 plus x squared. Well, what does x need to be to give you that 5/4? Well, x is 1/2. So I'm telling you that that information is leading you to know that x is 1/2. Okay? And so that's pretty tricky in this case. So what you need to look at now is this series. Okay? If you look at this series for when x is 1/2, when does the error become less than 1 over 100? Okay, and this term here is 1/4. Okay, so that's 1/2 squared. That's minus 1/2 times 1/2 to the 4th. Okay, so that's 1/16, 1/32, and that's not going to be big enough. And then plus 1/3, 1/2 to the 6th. So that was 1/16. This is 1/64 times 3. So this guy right here is less than 1 over 100. Okay, so this A thing is the approximation. So if this is the approximation we use, and this is just some number, right? This is the number A. This is the rational number that they want. This thing minus the function gives us an error of less than 1 over 100. Okay, you got to step through that again. Remember, the error is the next term. So I went through f of x right here. Right here. I went through the series I found and went 1/2 with 1/2 and 1/2 and 1/2, and I looked at the terms. Once I found a term less than 1 over 100, I knew that was the error, and then I could use this as the approximation A. Okay, and then this is some number, meaning I need to find A. So A does in fact equal 1/4 minus, what did we say that was? 1 over 32. That's 8 over 32 minus 1 over 32, and you get 7 over 32. That is what A is equal to. That's a hard one. If you look at a key, you get a point for figuring out that you need to use 1/2. You get a point for finding A, and then you get a point for justifying the fact that the error is what it is. Okay, so I get it. This one's a hard one as far as part D. I don't think part A is very hard. It's geometric. Part B is asking you when the geometric series converges, and we know it doesn't converge at 1. Part C is asking for a Maclaurin series or to understand the derivative or the integral connection between these two things. Part D is pretty hard. So fine, missed that one. You still get a 6 out of 9. That's still enough for a 4 or 5, depending on how you do your other ones. So the area one is almost always part C or part D. It's not worth a ton of points, but maybe you can at least get some partial credit on it, realizing that this difference in the absolute value is talking about the error. You're looking for the error term. You know the error term. Again, if it's an alternating series, you're looking for that next term. So go back to your function. See when this term becomes less than 1 over 100, and I happen to be that term. So then I can use those two terms. Okay, that's 2008.